Welcome back, everyone. I am absolutely thrilled to have you here for today's explainer. We are stepping into the incredibly high-stakes world of artificial intelligence. But, we aren't talking about chatbots writing emails today. No, we are talking about how AI safely governs and interacts with actual, physical, and logical enterprise infrastructure. Imagine the sheer panic of an LLM hallucinating a firewall rule change that literally brings down your entire cloud environment, right? When an AI system has its hands on the levers of your network, the most important question isn't just how smart is it? The real question is, how does it validate its actions before pulling the trigger?
To really understand how the SolveForce AI architecture tackles this massive challenge, we're going to follow a highly structured cognitive roadmap today. We'll start by meeting the digital helmsman. Then, we'll map out the context graph, climb the 5 infrastructure pillars, cycle through the rigorous 16-step reconciliation process, and finally, we'll explore how the system achieves validated learning and coherence. Let's get right into it.
Section 1. The Digital Helmsman. So why do we actually need a specialized AI control plane in the first place?
Well, imagine it's 4:45 p.m. on a Friday. You're running a massive multi-cloud enterprise network. An automated system receives a deceptively simple command: restart the service. Or maybe block the agent. Sounds straightforward, right? But think about the cascading danger of blind execution here. Which service exactly? In which environment? What dependencies are going to immediately crash if that service goes offline? If an AI just guesses based on statistical likelihood and, guesses the wrong dependencies, boom, you take down your entire payment gateway right before the weekend. You are literally one slight misinterpretation away from a catastrophic system outage.
This is exactly where we have to look at the fundamental difference in approaches. Legacy AI basically operates on reckless guesswork. It matches a text pattern, spits out a statistical confidence score, executes the action, and then just logs it after the fact, kind of crossing its fingers and hoping for the best. The rigorous, meaning-driven approach of the SolveForce AI pragmatics layer works completely differently. It doesn't just guess, it resolves the core intent, establishes a clear line of observability, and crucially, it verifies authority before a single byte of execution ever happens.
The whole architecture relies on a concept called the Kybernetes. It's a Greek word that translates to a digital helmsman, and honestly, it is a perfect analogy. Think of a ship's helmsman. They don't have unrestricted control to just steer the vessel wherever they feel like based on a whim. They are bounded. They continuously check their compass against the authorized, predetermined map. They're constantly reconciling the actual state of the ship, where it currently is in the physical water, with the desired, policy-governed course. And that is exactly how this AI operates within your network, constantly measuring reality against policy.
When you look at the macro view of the unified intelligence architecture, pay close attention to exactly where the pragmatics layer sits. It's positioned perfectly to take all the lower layer meaning, from the literal physical wires all the way up through network syntax and human semantics, and coordinate that collective meaning into safe, governed action. It's the absolute crucial bridge between simply understanding a situation and actually doing something about it safely.
Section 2. Mapping the context graph. So how does the AI actually build that incredibly deep understanding?
See, SolveForce doesn't just rely on a simple text embedding, not even close. It constructs a massive, multi-dimensional context graph across 8 specific dimensions to lock down a command. It meticulously resolves identity, entity, topology, time, domain, intent, authority, and consequence. You just can't ask who authorized this if you don't first know what exact asset is being touched and where it dynamically sits in the network. For instance, the system simultaneously resolves the exact server, the entity, and its exact location, the topology, before it even begins to question authority. A command remains completely non-executable until every single one of these dimensional boxes is firmly checked. No exceptions.
Section 3. The 5 infrastructure pillars. Because once the AI understands the context, it needs an unshakable foundation to actually interact with.
This foundation is called the reverse forward corroboration model. At the absolute base, step 1, we have the signal. That's the physical state, like the actual optical power on a fiber line. Step 2 is grammar, which covers the permitted connectivity rules. Step 3 is syntax, the structural composition of the network itself. Step 4 is semantics, locking down identity and meaning. And finally, at the top, step 5, pragmatics, where the contextual action happens. The absolute awe-inspiring technical achievement here is bidirectional corroboration. If a semantic command comes in to isolate a server, that action at the top traces all the way down through syntax and grammar until it verifies the physical optical signal on the fiber line at the bottom. It's incredible.
Section 4. The 16-step cycle. This brings us to the real climax of our explainer today, how an action is actually validated and executed.
Now, the SolveForce white paper outlines a highly complex 16-step recursive cycle, but we're going to zero in on the absolute most vital checkpoints today, because this right here is the core of how AI safely validates network actions. Before the AI touches your live network, it resolves the exact semantics. Then, and this is a massive leap forward, it actually simulates the effects and counterfactuals in an isolated sandbox. It's not guessing, it forecasts the exact blast radius. Will restarting this service drop active BGP sessions? Will it violate compliance? The system meticulously maps out the consequences first. Only after the simulation comes back clean does it seek strict authorization. And even then, it doesn't just fire and forget. It executes within strict, predetermined bounds and then independently verifies the actual post-execution state against what it originally predicted in the sandbox. If the prediction and reality don't perfectly match, it instantly flags the discrepancy. It is a continuous, rigorous, closed loop of safety.
Section 5. Validated learning and coherence. What exactly happens after an action is taken?
When an anomaly happens in a network, legacy systems might just blindly update a runbook and try the exact same failed script again. But not here. The SolveForce system meticulously decomposes deviations into 7 highly specific error categories. Is it a state error, where the hardware actually failed? Or is it a measurement glitch, where a sensor is just reporting the wrong data? Or maybe the language was perfectly understood, but the underlying intent was completely missed. That'd be a pragmatic error. By isolating the exact type of error, the anomalous result goes to the correct corrective mechanism. If it's a policy defect, for example, you don't rewrite the code, you trigger a governance review. It's an incredibly precise, smart way to manage failure.
The crucial anchor for all of this is the bidirectional coherence axiom, which states everything sent forward must remain verifiable backward. For network engineers, the stakes here are absolutely massive. This means no more black box AI behavior, where the system just learns a bad habit and you have literally no idea why. The AI strictly prohibits direct, automatic modification of its core models based purely on an anomalous result. Instead, that result undergoes a reverse causal reconstruction and independent validation. It basically guarantees that you have a perfect, verifiable autopsy of every single machine-learned lesson.
We've covered a tremendous amount of ground today, tracing a single command through some really rigorous verification layers. And it all boils down to a fundamental question. Is your infrastructure merely reacting to triggers, playing a dangerous game of guess and check? Or is it truly intelligent? True pragmatic intelligence doesn't just act. It deeply understands context. It verifies authority, simulates consequences in a sandbox, and leaves a flawless, verifiable audit trail. I really hope this explainer challenges you to demand a whole lot more from the intelligent systems guarding your infrastructure. Thank you so much for learning with me today, and I'll see you in the next explainer.